This podcast deals with electrochemistry, specifically with drawing voltaic cells. Again, I hope this is recording correctly because I've been having trouble with my microphone, but I want to go ahead and get this out there so that you can study for your test next week. So, the confusing part about this is that there's a lot of vocabulary that goes along with electrochemistry and drawing voltaic cells. I can also call them galvanic cells. So a galvanic cell is something that produces electricity by itself. It's spontaneous. And in spontaneity or spontaneousness, that was good, that means that positive volts are produced. What are negative volts? Well, I don't know, but negative volts never power anything. So if something produces volts by itself, then that is a voltaic or a galvanic cell, named after Luigi Galvani. Now, this site you see right here, this image, I actually have a link in this podcast so you can look at it later. But if you look right here, these are two different versions of a voltaic or a galvanic cell. And specifically, what a voltaic cell has are these parts, and we're going to learn some vocabulary, but this is called a salt bridge, or I can also have what's called a porous disk. There are two sections. There are half cells. So this is a half cell, and this is a half cell. It makes an entire whole cell. So, makes sense, right? 1/2 and 1/2 equals a whole. Again, 1/2 and 1/2. And if you notice, there's oxidation and reduction that's going on in each of these cells. Here's oxidation, and here's reduction. There's lots of vocabulary that goes along with this, and we're going to go ahead and use all these words. If you want to pause this, you can. And, of course, you need to be very comfortable with this oil rig where, whoops, pick a color and it doesn't do it. Here you go. Oxidation is the loss of electrons. And reduction is the gain of electrons. And remember, we talked about why that's important, because if you and I say reduction, I think world's biggest loser, I'm thinking of reduction as loss, when indeed it's the gain of electrons. So it's really important when you do this that you know oil rig. All right, and I'll do another podcast later that talks about how you determine oxidation and reduction in a chemical equation. But this is assuming that you understand this. So going to the next page, this is called a standard reduction potential chart. It's got a little zero here. If you look, well, it doesn't say, sorry. Most of these have a little part at the top that says E0. And so standard, this standard means that it's at 1 atmosphere, 25 degrees Celsius. See, that says this right here, doesn't it? And that these solutions are on 1 molar. There's 1 mole in a liter. And that's what this potential voltage is. This E0 means electromotive force, overall cell potential, or the key thing here is volts. So if you look back here, that's where all these volts are. So each of these substances is undergoing reduction. How do we know they're undergoing reduction? Well, if you look, here's a substance and there's an electron, and it's making something new. Here's a substance and an electron, 2 electrons, and it's making something new. All of these are catching electrons, aren't they? In other words, all the electrons are on the reactant side, making something new on the product side. So let's look at this. And let's look at this zinc +2 zinc electrode, and copper +2. I'll explain what that means in a minute. Copper electrode, or cell, excuse me. So if you look, I have, and this is already made, so I'm going to walk you through how this works, and then I'm going to show you how to draw it in a different cell. So we have an anode right here, and we have a cathode. And if you look, this anode is solid zinc, and this cathode is solid copper. And there's their salt bridge, which we talked about parts-wise. And these are electrolytes. So this is a zinc nitrate solution, and that will be aqueous, which means it dissolves in water. And this is also an electrolyte on this side. And so it's a copper nitrate aqueous solution, which means it dissolves in water. There's a voltmeter, which shows flow. And the flow of electrons goes from the anode to the cathode. Okay, or fat cat. From the anode to the cathode is the direction of electron flow. Now, what's right in the word anode? there's an N. That is a negative electrode. We're going to call it a negative electrode. And what happens there? Oxidation. Okay, so you can picture an ox. This is looking like a bad anime bunny. There's this evil ox coming down the hallway at me, and it's got negative eyes. It's going to hit me. It's going to run me over. So that anode is that negative electrode. Now what's a cathode? And I should be using different colors, but I'm not, sorry. I'll do this over and have a better microphone going on here. This is reduction. It occurs at a cathode, right? Red cat. And so this cathode is positive. Positive, like a kitty cat. Make sense? Right now, I'm going to go ahead and get rid of all this stuff, which means I got rid of my copper and my zinc. But I know that I'm looking for copper 2+ and a solid copper electrode, or I'm looking for this combination, I should say, and zinc 2+ and a zinc electrode. So I'm going to look at my standard reduction potential chart, and I'm going to find zinc, and there it is right there. See this right here? And copper, you have to be careful because copper is a bunch of different charges. Well, of course, this chart is only one, and so here's my other selection right there. So I'm going to go ahead and copy this down and get rid of this. I'm going to copy both of these reactions, and I'm going to go ahead and use different colors so you can see them better. I'm going to copy them down as is. So I'm going to write Cu 2+ aqueous. All I'm doing is copying this down out of the chart. Plus 2 electrons make solid copper. That's one. Now what's my other one? My other one is zinc 2+ aqueous. Plus 2 electrons make solid zinc. Now what are my values? My values for this are negative 0.76 volts. And what's my value for my copper? Positive 0.34 volts. So all I've done is copy each of these onto a separate sheet of paper, or right here. Now, you're going to look at this standard reduction potential chart, and you're going to say to yourself, am I positive I'm being reduced? Am I positive I'm being reduced? That means whichever number is the more positive number is actually being reduced, and the other half reaction that you've copied is being oxidized. So let's look at these. You have positive 0.34 volts and negative 0.76 volts. I sure think that this is more positive than negative 0.76 volts, don't you? So I'm going to go ahead and I'm going to copy them down right here. And actually what I should do is just move this out of here. How about that for fancy? Actually, you know what? Let's go back to the other page and I can do that over here just as easily. Okay? That way you can see it. So if you look, what am I going to do? Am I positive if I'm being reduced? So in other words, this is being reduced. And this is being oxidized. Come on. This is being oxidized. Now what's that mean? That means that I physically need to take that zinc reaction and I need to flip it. And why do I need to flip it? Because didn't we just say that these are all written as reduction? There's both reduction, aren't they? So I'm going to go ahead and I'm going to take this, I'm going to cross it off. I'm going to completely flip it. So that my zinc is on this side. And my zinc plus 2, let me go ahead and write these as, and my 2 electrons are on this side. And now I'm going to switch my voltage. Now what did I do? I rewrote this equation because now it's being oxidized. See these electrons right here? They're being lost. They're going away. These electrons right here are being captured by the copper 2+. So how do you do this again? You look at both of these. Let's see if I can grab this. I don't know if I can. It's all the way down here somewhere. Nope. It's gone. Okay, so let's go back over here. This whole chart is written as reduction. I need to put my hand on both of them and say my positive I'm being reduced. I looked at copper in this case, and I looked at zinc. This is more positive, so I leave it as is, as a reduction. I completely flip this, and changing it, I'm going to change the sign to positive, and now it's being oxidized. Okay? So let me erase this. All we did was reverse the reaction to turn it around So that now we can look and we can say, which one of these is being oxidized? Well, if you look, this is being oxidized right here, and this is being reduced. How do you know that? Well, let's add this up and have an overall cell reaction, okay? Let's figure out what this total reaction is. What's really going on? I'm going to put my arrow right here, okay? And my electrons that I start with, I also end up with. So they're not part of my reaction whatsoever. But what do I have going on? I have copper 2 plus, aqueous. All I'm doing is adding these up. And zinc solid. And what's happening to them? Well, copper solid, it doesn't matter which order you write it in, is here, and zinc 2 plus is here. Did you see that? So I just copied exactly what I wrote down here. My electrons are balanced, so I don't need to include them. They make this happen, but they're not part of the overall reaction because what you start with and you end up with you don't need to use. And my overall voltage, if I was to add this up right here, that would equal 1.10 volts. And it's positive, isn't it? It's positive, and that's important because that positive 1.10 volts, which is my total E0 for my entire cell, is 1.10 volts. That means that it's producing electricity and it's spontaneous. Because it's positive, it is spontaneous. This right here is the cell potential for my reduction half reaction. Do you see how this is a half reaction? And this is my potential for my oxidation half reaction. Do you see how this is a half reaction? And I took both those half reactions and I added them up, and I have my entire cell. And this is my overall reaction for my cell right here. And I have 1.10 volts. And that's what you write E0 cell because you got this off a standard reduction potential chart. So there you go. There's my overall cell, right? I add those up and get my total reaction. I'll do that one more time for you. So copper 2 plus, and if I see this right here, I know that's aqueous because they're ions, plus zinc. Make zinc plus copper. It's real important to write those states of matter. Now, let's go ahead, and if you don't want to do this part, you can just go ahead and move on. But I'm going to go ahead and just show you exactly what's happening here. Here's my zinc, and here's my copper. What's happening? This is going from 2 plus, or plus 2, to 0, which means it's gaining electrons, right? And we said that this was my reduction half reaction. How about that? So that's gaining. And what's happening over here? This is going from 0 to 2 plus, so this is losing electrons, which means oxidation, right? And this was my oxidation half reaction. So how about that? It all matches up, doesn't it? Now, this is my overall reaction again. I'm going to write it here so you can see. I'm writing in colors so you can follow what's happening. And we're going to go ahead and label this cell. So, my zinc is being oxidized. That means that goes at my anode. So my anode is my zinc. I'm going to call it negative because there's an N right in there, right? So that's negative, and I need to put that that's a solid. That's really important because that determines where my electron flow is. So I instantly know that my electron flow is going in this direction, right here, right? Fat cat, from the anode to the cathode. Now if I know that's my anode, what do I know this side is? This side is my cathode, and look at that, the plus is right in there. So this cathode is positive, and it's my solid copper. So this is my cathode right here. Now, the minute you have your electron flow, and I should really write electron flow here, what happens is you go back to your half cell reactions. So I'm going to take this, and I'm going to, then I have this electron flow in here like this. I'm going to go ahead and draw an arrow this way, and an arrow this way. And you'll see why in a second, okay? So let's go ahead and look at the half cell reaction at the zinc. Here's my half reaction. So I'm going to write this here so you can see it so it's bigger. Okay, that's a 2. All right? So what's happening in this anode? Oh, look, there's my electrons. They're flowing, and this is a solid. And look, you can see right here it's negative. Now, if you look for a second, what's going on? They have here, they show you that ions are leaving. So I'm going to go ahead, see this dot right here? These ions are going into that solution, right? Didn't we draw an arrow? We drew an arrow here, didn't we? Okay? They just have their arrow going in a different direction. They have this arrow looking like this, just so you can visualize. They have it going like this. See that right there? So what's happening in the solution is that ions are leaving. And look, here's your story. Here's my solid bar. Here's my electrode. What's happening? Through the wire, electrons are leaving. Oh, look, there's the electrons. And what's happening is more and more zinc ions are being produced. So where are they being produced from? This is my solid electrode. See this? The electrons are leaving through the wire. They're going this way. My zinc ions are going into solution right here, so they're actually increasing in concentration, and my solid zinc electrode's going down. And that's what a picture of this is. Look at the zinc anode. Look how much it's deteriorating. Why? What's happening? I've got zinc ions leaving, going into the electrolyte. That's why it's so important you have an electrolyte in that beaker, right? So you have a beaker right here, and it's full of an electrolyte, and that electrolyte happens to be zinc. And then you have a wire, and the electrons are leaving that wire. So let's look at the other side of the cell. What's happening? The electrons are coming through the wire from the anode to the cathode. They're entering, look at it, there's a plus right there to that cathode. That's solid copper. All right, and look what's happening here. Remember we drew an arrow right here, right? We drew an arrow going this way so that these copper ions are actually plating onto that cathode. So let's look at the half reaction here. Here it is. I'm going to copy it up here. Okay. I should just make a habit of making my 2's swoopy so you can understand the difference between Z's and 2's. So here you go. What's happening? So in my solution I have copper ions. The electrons come in, and you would think that the cathode is what's reduced, but it's not. This is reduced. We'll go back to that electrochemical cell overall reaction in a second. But that's reduced. So as every 2 electrons enter through this wire, what happens? The copper ions are attracted. Where are they going? They're going, see that right here? They're going here. It's kind of a weird picture the way they show it. Okay? They're going on here. They're actually plating the electrode. So what's happening is the copper electrode, look at this. It's got more stuff on it, doesn't it? That's because the copper 2+ ions, as the electrons are coming in this wire, the copper 2+ electrons are actually plating on here, making it so it's heavier. So the concentration of these in solution, these are going away. They're getting less. And the concentration of the solid electrode, the mass is increasing. If you want to watch this, it explains step by step. And so actually it's this picture back here, way back in the beginning, this one right here, this picture, it takes you through. It's wonderful. Okay? But while I'm here, let's go back and talk about this overall reaction that I wrote. Okay, and look at this diagram. So if you look, this right here is oxidized. This is oxidized. Right, my zinc is oxidized. So if that's oxidized, look what's happening in the beaker. This is what's in the beaker. See this right here? My zinc 2+. So what happens to my zinc? The solid mass goes down as electrons go through the wire, and the concentration of this goes up. That's why I put an arrow like this. What happens on the other side? My copper 2+ ions are what's reduced. In come the electrons. These are attracted. All right? And my solid copper is going up in mass. So if you look, my overall reaction, let me write it here again. This is before. And this is after. And I want you to remember that because it's really important when you draw a cell. So here's my cell. This is before. This is my zinc solid. And this is my copper 2+ ions here. This is oxidized. It's a negative anode. This is reduced. It's before. Now what happens after? I've got way more zinc 2+ ions in solution. Right? This is after. So this is what it looks like after. This is being oxidized. This is what it looks like after. And this is being reduced. Where's that? In my beaker right here, right? And what happens? The electrons come in through the wire and these plate on. So this is before and this is after. How about that? Now, there's something called line notation. And line notation is an abbreviation. By the way, there's a salt bridge in here. And the purpose of the salt bridge is for all these ions are building up and these are slowly going away. It's so that there's a flow of ions that take place, right? Electrons go through the wire. Ions can flow back and forth to reestablish that balance. So sorry, let's go back to line notation, which is a shortcut. So what happens? Let's take this to a different page. Okay? It's very simple. This is my anode, and this is my cathode. So what are they? My zinc is my anode, and I show a solid. My copper is my cathode. What's in my beaker with my zinc? My zinc 2+ ions. And what's my beaker right here? My copper 2+ ions. So that's all this is. It's a very simple depiction of what the cell is. From the anode, here's my anode, then this goes next. See that right there? Then this goes next, then this goes next. And by the way, if you go with our before, right? This was before. This is before. Those are my reactants. What are my products? These are my products. Right here, right? Here's my products. There's my products. How about that? Oxidized, reduced. What happens to both of them after? All right. Let's try another one. This is standard reduction potential chart, and right now I'm going to go ahead and do an aluminum cell. And I'm going to go ahead and, here's aluminum, right? And magnesium. And magnesium's not on this. Of course it's not. So I've went ahead and copied this up a bigger standard reduction potential chart. And if you notice, both of these are negative. Uh-oh. And the electrons don't match. Uh-oh. So here's a number line. Here's 0. Here's negative 1.66, and here's negative 2.37. So think about it. Which one's closer to 0? If you said this, then that's correct. So the larger, and my positive ion being reduced, there's nothing that's positive, but it's closer to 0. This is reduction, and this is oxidized, or oxidation. So reduction is the closer to 0 value, the larger value. So what's that mean I'm going to do? It means I take this and I flip it, right? And I write it completely backwards. All right, I'm writing it backwards. And in doing so, I'm going to flip the sign. All right, now, what's the deal here? Now I need to add this up to get an overall cell reaction. So I have aluminum 3+, and I have magnesium. This is aqueous, and this is a solid. There's my arrow, and there's my magnesium 2+, and there's my aluminum solid. But I have a problem, because if you look, I have 3 electrons being gained as 2 electrons are being lost. And actually what happens first? Oxidation happens first, and 2 electrons get lost and 3 electrons get gained. Ruh-roh, that doesn't match. So you need to balance this. So what's the common number they both go into? You say 6. So I multiply this by 2 to change this into 6 electrons, and by 2, but I don't touch these volts. I'll explain why later. Volts shock you, so do not touch them. No way, Jose. Okay? Now, what am I going to do here? I have 2 electrons here, which means I'm going to multiply this by 3 and this by 3 to make this 6. And now look what happens. My electrons cancel. I throw 6, I catch 6, and now I bring my numbers down from my balancing. And again, do I multiply by the volts? I multiply this by 3, this by 3, this by 3 to turn that into 6. Don't touch that. What's my overall voltage? How do you do that? Well, if you add them up, don't get the overall volts, and the overall volts happens to be 0.71. Is it positive? Yes, you say it is. If it's positive, it's spontaneous, it produces volts by itself. So here's the overall balanced equation. Let's go ahead and draw a cell. If this is oxidized, right, 0 to +2, right, and that was my anode, right? So this is magnesium. This becomes my anode. What charge is my anode? It's negative. Where's my wire go? Right here. What's my cathode? This is my cathode, aluminum. If that confuses me, I can go in order of before and after. So what's my before? Here's my magnesium. This is my before, right? Get rid of that one little mark there. Let's get rid of this so it's maybe not as confusing, or it's a different way. There's all kinds of ways you can do this. So what's my before? This is my before, isn't it? So where's that? That's in this beaker, isn't it? Right? This is oxidized. This is what's reduced. Now what happens? Well, electrons flow through the wire from the anode right here to the cathode. The cathode is charged positive, right? Red cat. And I can now establish my arrows since I already have my electron flow here. I can put an arrow this way and an arrow this way. That's my half-cell reactions, right? Magnesium solid electrode is actually decreasing in mass. Why? It's making magnesium 2+ ions. Look at that. And those are going into solution. They're increasing in concentrations as my electrons leave through the wire. So this is my half-cell reaction, isn't it? Look at that. See that? That's my half-cell reaction I have right here. Now what happens on this side? Well, my aluminum's being reduced. It's in my beaker. Electrons are coming in through the wire. And I'm making aluminum solid. So this is my cathode right here. My aluminum solid is my cathode. The concentration of these are going down. They're going away as the electrons enter. And the mass of this is going up. And that's it. Oh, wait, let's do line notation. Okay, this is a mess. So I've got magnesium, solid. Oh, I didn't have a salt bridge either, did I? And I've got magnesium 2+, aqueous, salt bridge or porous disc. And then in my beaker, I have aluminum 3+ ions, and an aluminum solid electrode, which is a cathode. And if you noticed, I do not put the balanced equation coefficients in here. This is simply telling you if you get a strip of magnesium and put magnesium 2+ ions, and aluminum 3+ ions and aluminum, you will have a cell that produces voltage of 0.71, and it's spontaneous because it's positive.